So we're back again to document the rest of the work to finish our new rocket and try it a test launch. Unfortunately, I kind of had limited time to finish working on the rocket, so I didn't get a whole lot of pictures or a lot of time to document the whole process. So we're going to take a really quick look at what I did to finish it out. So we took the rocket engine that we made last time, we added some small wings down at the bottom end, and we put a nose cone section on the top that includes the parachute recovery system. So this rocket has a side ejecting parachute. So there's a door to a parachute compartment on the side of the nose cone. There's a plastic spring in there to help push out the parachute, and we've got the parachute attached on a line there. We'll roll up the parachute nice and tight, squeeze it into the compartment, and shut the door using the rubber bands to compress it closed. The rubber bands attached to the air flap system on the side of the rocket that will release it when rocket hits apogee. This did reveal one design flaw in the rocket. I originally wanted to use a much bigger parachute because, of course, this is a larger, heavier rocket, so a larger parachute will offer more cushioning, more braking on its way down, and a better chance of recovery. Unfortunately, the compartment that I left for the parachute was too small for the parachute that I intended to put in there, so I'm using the same 20-inch parachute that I used for the rockets last year. On the other side of the nose cone, we've got a compartment with some bracing and a small flap of a door that we can nicely secure our altimeter in, so it won't be going anywhere, and it'll have enough airflow that it gets good readings. Before we launch, this flap will be duct taped down and closed just so the altimeter can't go flying out. And you'll also notice I did anchor a rubber band to it. That rubber band is going to help pull open the door to make sure that we get maximum clearance for our parachute as it comes out of the compartment. The plan for our onboard camera is basically the same as what we did last year. We're going to just tape it to the side of the rocket pointing down. I'm going to try and tape it to the side opposite of where the air flap is, just so that the little break and wind resistance it's going to give me should match and balance out with the air flap. And finally, we see the whole rocket assembled and ready to be put on the launch pad. We're going to use the same exact launcher that we did last year. Again, all the sizes will fit. Just have to watch the balance a little, just because it's a much taller and heavier rocket that's going to be sitting on top of this thing. And now with the rocket sitting on the launch pad, ready to go, you can see that the rocket in launch position is about the size of a 9-year-old. So this is significantly bigger than our previous rockets. We're all set to go with 1.5 to 2 liters of water in the rocket, which is about a third of our volume. We're going to pressurize it. We're going to try and hit somewhere between 50 and 60 psi and see what happens. So a larger rocket means a lot more pumping on the bike pump. So we're going to have a short little cut in here so you don't have to see the whole long sorted thing.
Oh! Oh my gosh. That happened.
And so our first test launch was a failure. We had a significant structural failure. The rocket actually split in half, and the top section rocketed off into the sky. Not too high because there was no water in that section, so this was just air pushing out. The positives, the parachute did deploy and cleared the doors nicely, and the top section of the bottle made a nice soft landing, even though we didn't get it on camera. The point of failure is pretty obvious. It was the tornado tube connecting the two sections of the engine together. The tornado tube itself and the threads on the bottles didn't look like they were damaged. It was just enough pressure to just pop it off like a bottle cap flying off of a bottle. In fact, exactly like a bottle cap flying off of a bottle. While I could potentially reuse this tornado tube because it doesn't look like there was any real damage, I'm going to actually replace it with a different tube just to make sure that it doesn't have any structural weaknesses or cracks hiding in it that are going to be a problem later. So the fix for this is pretty obvious. The tornado tube is making a pretty good seal, otherwise we wouldn't have got the pressure up to 40 psi, which is where it was when it let go. So we can look at what failed and what didn't fail, and that's going to give us some clues on how to solve this problem. What didn't fail is the glue joint between the two bottles that we split to make the larger of the two engine compartments. So we know that that construction glue can hold at a higher pressure than where we had our failure. So we're going to do the obvious. When we replace the tornado tube, we're going to take some of our PL Premium construction glue and we're going to put it on the threads inside the tornado tube on both sides where the bottles are going to twist in. We're going to twist them in just like we did originally, let the glue set for at least 24 hours, and then we'll be ready to rock and roll and take another stab at this. So thanks for watching. Hope you had fun watching us fail miserably in our first test flight for our new larger rocket. And we hope you'll join us next time when hopefully we get a really good flight to show you and some good metrics and other camera views and all that good stuff that we usually get for the other rockets. Thanks a lot.